Welcome to the new video of our channel. Hope you're all fine after the big internet outage yesterday. In this video, we'll talk and inform you about web cloud outages and global network resiliencies in 2025. So, yesterday was rough. The internet just sort of broke.
Yeah.
And it wasn't just a small flicker, was it?
Not at all. It was a systemic failure.
Exactly. We saw this massive worldwide hiccup on November 18th, 2025. And when services like X, formerly Twitter, and OpenAI's ChatGPT, even Spotify, when they all start throwing up error messages at the same time.
It stops being a coincidence.
Right. It's not some local problem anymore. And I think that realization that something as simple as checking your feed or, asking an AI a question depends on this huge, complex web of systems all working perfectly. That's what we really need to break down today.
It was a frustrating day for, well, pretty much anyone trying to get anything done online. And as we start to look at the technical reports and the postmortems that have been shared, our mission for today becomes really clear. We need to systematically break down these highly technical systems that our modern internet just completely relies on.
And we need to do it in a way that everyone can understand.
Exactly. We're going to make sure that even if you're totally new to technology, you'll walk away from this understanding what terms like the cloud or anycast or a control plane failure actually mean. We'll explain it clearly, calmly.
So you can really get what happened.
Yes. So you can grasp why these massive distributed networks are still so vulnerable and what companies can actually do to stop this from happening again. We're analyzing all the sources that have come out to really understand what happened and, more importantly, why it matters to every single one of us.
Okay, let's do it. Let's unpack this and start at the very, very beginning. We hear the term the cloud constantly. It's everywhere in tech conversations now. But if we strip away all the marketing, what is the cloud really from, say, a networking point of view? And just how deeply is it actually integrated into our daily lives?
That's the fundamental question, isn't it? The cloud is such a deceptive name. It makes you think of something abstract, maybe a bit ethereal.
Right, like your data is just floating up in the sky somewhere.
Exactly. But in reality, it's just massive interconnected computing infrastructure.
Right.
We're talking about hardware, storage, and software, all living in these giant data centers that are owned by a few huge companies. And to really appreciate what the cloud does, you first have to understand the problem it was built to solve.
Okay.
So let's start with the old way the internet delivered content. This was all based on a concept called the origin server.
So an origin server is basically the home base, right? Where a website's files and all its data originally live.
That's it, precisely. In the early days of the web, if you hosted a website, it lived on one physical computer, or maybe a small group of them. We called that the origin server. And it was usually located somewhere central, big data center in New York or London.
So if I was trying to get to that website from, let's say, Johannesburg in South Africa, what was the technical hurdle there?
The main hurdle is, and always will be, physics. It's just distance and time. When your computer requests content from a website, the code, the images, the videos, that request has to physically travel.
Through fiber optic cables under the ocean and everything.
All of that. It has to cross continents to reach that one origin server. And then the response, with all the data you asked for, has to travel all the way back to your device.
And we measure that travel time in milliseconds, but it adds up.
It really does. That total time for the round trip is called the round trip time, or RTT. When the RTT is high, say 300 or 500 milliseconds, the page just feels painfully slow to load.
And that was just one problem. What about traffic?
That was the other huge issue. Traffic overload.
Huh.
If that website suddenly got really popular, maybe a big news story broke, that single origin server would get completely overwhelmed by millions of people trying to access it at once.
And it would just fail.
You would fail. You'd get timeouts or those 503 service unavailable errors. That whole centralized model was just fundamentally unsustainable for a global high-traffic internet.
It couldn't scale.
It couldn't. So the only real solution was to take distance out of the equation. And that's really the driving idea behind the Content Delivery Network, or CDN. And the CDN is the core concept of what we call the web cloud.
Okay, so tell us how a CDN changes that whole equation.
Well, a CDN isn't one single location. It's this huge interconnected web of servers that are deployed all over the globe. We call these individual servers edge nodes or points of presence. And they're strategically placed in hundreds of major cities, really close to where people actually live and work.
So the whole idea is to move the content closer to the user.
Exactly. A CDN's primary job is to cache content. That means it takes temporary copies of the website's data from that faraway origin server and stores them on these nearby edge nodes.
Ah, Okay.
So when you request a web page, your request gets intercepted. It's redirected to the nearest edge node. That node checks its local storage, its cache first. If the content is right there, it serves it to you instantly.
So your request only has to travel maybe a few miles to the nearest city instead of halfway across the world.
That's it. It drastically reduces the RTT. Your request might only travel 10 or 20 milliseconds away instead of across an ocean. The difference in speed is just enormous.
That's a huge improvement for speed. But you mentioned the web cloud does a lot more now than just speed up images and files. How else is it integrated into our lives?
Oh, its integration now is just pervasive. It spans everything from security to application logic. The cloud is now responsible for handling these massive security challenges. For example, it provides DDoS mitigation.
That's when attackers flood a website with junk traffic, right?
Yes, a distributed denial of service attack uses millions of compromised devices to just overwhelm a target. The CDN, with its huge global capacity, just sits in front of the real server and absorbs all of that attack traffic. It protects the actual website.
So it's like a shield.
It is. And it also acts like a digital police force through something called a Web Application Firewall, or WAF. The DIA inspects every single piece of traffic, looking for malicious patterns, and it blocks common web attacks before they could ever reach the customer's actual server.
And what about modern apps, like ChatGPT?
That's where it gets even more integrated. For modern applications, things like serverless computing, APIs, and all the processing power you need for AI models, the edge nodes themselves now execute code. They run complex application logic right there, close to the user, for maximum speed.
So it sounds like the web cloud isn't really optional anymore. It's the mandatory infrastructure you need to just survive on the modern internet.
It's an absolute prerequisite. The key insight here is that this architecture creates a consistent performance envelope all around the world. If the CDN is working right, a user in São Paulo should have roughly the same fast, secure experience as a user in Seattle.
Even if the actual website is hosted in Dublin.
Exactly. But, and this is the critical point we keep coming back to, that massive global consistency depends entirely on the centralized logic that governs that distributed network.
And that consistency brings us directly to the companies who manage this infrastructure, and specifically to Cloudflare. They were right at the center of the outage yesterday.
Yes. Cloudflare is, I would argue, the single most critical backbone of the modern public internet. They sit in front of a huge percentage of all global web traffic.
So if they are the backbone, what is their core function exactly? What's their story?
Cloudflare's core service is to function as a reverse proxy. The easiest way to think of it is as a highly sophisticated global checkpoint for traffic.
So when I try to go to a website using Cloudflare, my request doesn't go straight to the website's server.
That's right. It hits the nearest Cloudflare edge node first. Cloudflare sits right in the middle between you and the origin server.
So they're kind of like the traffic cop, the security guard, and the librarian all rolled into one. They check every request before deciding what to do with it.
That's a great analogy. They inspect it, they speed it up using their cache, they apply all the security checks like DDoS protection and the WAF, and then only if the traffic is legitimate and isn't something they have cached, they pass the request on to the customer's origin server.
Their whole goal is to maximize performance and minimize threats.
Yes, and their history shows this pattern of just incredibly rapid growth and adoption. They started with CDN and DDoS protection, but they got massive public visibility when they launched their free public DNS resolver 1.1.101 back in 2018.
I remember that. It was a big deal.
It was huge.
Yeah.
Because it was privacy-focused and extremely fast, it quickly became one of the most popular DNS services in the world. And that brought millions of new users onto their infrastructure, massively expanding their footprint.
So when we look at their scale today, protecting over 4.6 million websites, what does that actually mean for the average person's day online?
The numbers are pretty staggering. The sources we're looking at suggest the average internet user interacts with Cloudflare services hundreds of times per week.
Hundreds, wow.
Every time you load an image on social media, stream a video, use an app that relies on an API, or even just look up a website name using 1.1.1.1, you are probably hitting their network. And that scale means they've become a single point of failure for huge chunks of the digital economy.
And this whole massive system is built on a technical principle that's designed for redundancy, right? Anycast routing, it sounds complex, but it's really important for understanding why yesterday's failure was such a shock. Can we break Anycast down simply?
Absolutely. Anycast is the foundation of their high availability.
Right.
If you think about traditional networking, it uses something called unicast.
Unicast, I don't know.
Unicast just means one IP address points to one specific physical server. If that one server fails, that IP address is just unreachable. Game over. Anycast is fundamentally different. It cleverly uses the Internet's core routing protocols, mainly Border Gateway Protocol, or BGP, to achieve this incredible redundancy. Instead of one server, Cloudflare configures hundreds of their data centers all around the world to announce the exact same IP address to the rest of the Internet.
So it's like putting the same unique phone number on 100 different phones scattered all over the globe.
Hmm.
How does the call know which phone to ring?
That's the magic of BGP. BGP is like the GPS of the Internet. It manages all the traffic routes between the big networks. When your request leaves your computer, BGP looks at all the different locations announcing that one Cloudflare IP, and it automatically routes your traffic along the path it thinks is best.
And best usually means closest, I assume.
In practice, yes.
Hmm.
It usually translates to the path of shortest network distance. So your request is automatically routed to the nearest healthy data center that's advertising that IP.
So if the Paris data center is the closest one to me, my request goes there. But what if, say, the Paris data center has a major hardware failure? Catches on fire.
The Anycast system provides immediate, built-in redundancy. If the Paris data center fails, it instantly stops announcing that IP address via BGP. The rest of the Internet very quickly recalculates the shortest path, and your requests are instantly and automatically rerouted to the next closest healthy node, maybe Frankfurt or Amsterdam.
And the user barely notices.
The user might experience a fraction of a second of turbulence, but the system just routes around the problem, all without any human needing to do anything. It's incredibly resilient against external attacks or localized hardware failures.
Which makes perfect sense. The whole design is supposed to be almost foolproof because it's so distributed. And yet, yesterday, November 18, 2025, we saw this massive distributed system fail on a global scale. So let's shift our pace here, calm and slow, and really detail what happened behind the scenes.
Okay. The incident began almost instantaneously across the entire globe, shortly before 12.00 UTC. Cloudflare sent out their first alert at 11.48 UTC, confirming they were investigating an internal service degradation. And the key word there is internal.
And the immediate symptoms for us, the end users, were really striking. It wasn't just small websites going down.
No, absolutely not. The outage hit services in these critical high-impact areas, AI processing through OpenAI and ChatGPT, global communication on X, media streaming on Spotify. The failure wasn't selective. It was just pervasive.
And the most ironic part was Down Detector going down.
Yes. Perhaps the most illustrative symptom of this whole concentration of risk was the intermittent failure of Down Detector itself, which ironically relies on Cloudflare for its own operations. It was like the Weather Channel going down because of the storm it was supposed to be reporting on.
And what was the technical error code that everyone was seeing?
Users saw widespread HTTP 500 errors. And we should be very clear for anyone new to this, that's a server-side error. A 500 error means that Cloudflare Edge node received your request successfully.
So the connection was made.
The connection was made, but then the server itself malfunctioned internally. It couldn't execute the logic or the policies it needed to in order to fulfill your request. And that's fundamentally different from a connection just timing out. It signals a deep operational failure inside the servers themselves.
So if Anycast is designed to route around localized physical failures, a global 500 error suggests the problem wasn't physical at all. It was logical. It was in the brain of the network, not the body.
That is the critical realization. And what made the November 18th incident so severe was that the network's brain and its body failed at the same time. We have to distinguish between two layers of the infrastructure, the data plane and the control plane.
Okay, let's break that down. The data plane first.
The data plane is the engine. It's the part of the system that does the actual work, moving the data packets, serving the cached content, applying security checks, and sending requests onto the origin. When users saw those HTTP 500 errors everywhere, that was the global failure of the data plane. The edge servers were just incapacitated.
And the control plane. That's where all the management happens, right?
The control plane is the central nervous system. It handles all the management, all the configuration updates, the monitoring, the administration. It's the Cloudflare dashboard and the API that customers use to change their settings. And the critical problem yesterday was that the control plane failed at the exact same time as the data plane.
So not only were the websites down, but the network administrators, the very people who needed to fix the problem, were locked out of their own tools.
Precisely. They were flying completely blind. They couldn't access the network or trigger any emergency actions through the API or the dashboard. Even their own public status page, which is also managed by the control plane, was broken. It kept losing its styling, which made it even harder to communicate what was going on.
That dual failure must have just massively compounded the problem.
It did. It severely increased the time it took to fix everything.
So, if the Anycast system is built for physical redundancy, how on earth could a single problem spread across hundreds of data centers globally at almost the exact same instant?
The early analysis, based on the pattern of the failure, points very strongly to a centralized software flaw. And this really highlights the paradox of these systems. The physical network is distributed and resilient, but the logical layer that governs it, the system that deploys configurations, is by necessity centralized.
So, what's the leading theory?
Well, the consensus, what we're calling hypothesis 1, most probable, is an internal configuration deployment error.
Okay.
So, imagine a single corrupted configuration file, maybe a file with rules for routing or some edge logic. This file is designed to be pushed out to the entire global fleet of servers at once. If that configuration contained a fatal flaw, some instruction that caused the servers to crash,
That flawed update would be instantly propagated everywhere.
instantly, overriding the working logic on every single edge node and completely defeating the physical resilience of the Anycast network.
That's the Achilles heel of these hyperscale systems, isn't it? The ability to deploy globally in an instant is a huge advantage until you deploy a fatal error.
And we found a really crucial clue that links this to a routine operational task. The initial failure was reported at 11.48 UTC. That is extremely close to the start of a scheduled maintenance window in the Santiago, Chile data center, which was set for 12.00 UTC.
That can't be a coincidence.
It's highly unlikely. It suggests that some operational change related to that planned maintenance, maybe shifting traffic or preparing software, inadvertently triggered the propagation of this catastrophic flaw across the entire global network.
So what was supposed to be a low-risk, controlled change for maintenance in Chile ended up bringing down social media and AI services for the entire world.
That's the gravity of this kind of concentration. It really underscores how any small operational activity in a system this large carries a potentially global blast radius if the change management process fails.
And we saw specific action during the recovery. They temporarily disabled something called warp access in London. What does isolating a feature like that tell us?
Warp is Cloudflare's client-side application. It's used by consumers and businesses to secure and speed up their personal internet connections. It relies on some pretty advanced internal routing.
Okay.
So temporarily disabling components of it suggests that the engineering team was trying to isolate these advanced virtualized routing features. It confirms that the problem was spreading deep inside their internal systems, the ones responsible for service integrity and complex routing. It just adds more weight to the theory of a sophisticated internal configuration error. This failure, where a single configuration change can take down a globally distributed network designed specifically to withstand failure, raises serious existential questions about how we manage and govern our core internet infrastructure. The redundancy is physical, but the decision-making is logically centralized.
Hey, listener, do you have any other idea or question about this? Please write in comments so we can discuss. The November incident, as dramatic as it was, unfortunately wasn't an isolated event in 2025. When we look at the other major outages this year, we start to see these recurring patterns emerge. And that leads us to a discussion about the relationship between Cloudflare and other giants in this space, specifically Amazon Web Services, or AWS.
Right. The relationship between Cloudflare and AWS is complex. They have similar goals in providing infrastructure, but they play very different roles. And, to be clear, they're completely separate companies.
So how do they fit together?
Well, AWS provides the foundation. They provide the hosting, the computing power, the databases. Often, they are the origin server for a customer. Cloudflare, on the other hand, acts as the global reverse proxy that sits in front of that origin, providing the security and acceleration, whether that origin is on AWS or Google Cloud or anywhere else.
So they have to work together. A lot of traffic has to pass between them.
A huge amount. They are highly reliant on each other for traffic exchange.
Okay, so let's analyze the other incidents from this year to map out these vulnerabilities. Let's start with the AWS congestion incident on August 21, 2025. This wasn't a global Cloudflare failure, was it?
No, the sources are very clear on this. This was a regional congestion problem. It was centered squarely on the physical connections, we call them peering links, between Cloudflare's network and AWS's massive East 1 region in Virginia.
Which is a huge internet hub.
One of the biggest.
So what caused the pipes between these two giants to just clog up?
The root cause was a classic capacity problem under stress. A massive and very unusual traffic surge from a single Cloudflare customer was all being directed towards that one AWS facility. And this one flow of data was so huge that it completely saturated the direct physical links between the two networks.
So it wasn't a software bug like in November, it was just pure volume overwhelming the physical connections. What did that look like for users trying to reach services in that AWS region?
They would have experienced high latency, severe packet loss, and connection failures. Just classic symptoms of a clogged network. And it's important to note the difference. They weren't getting those systemic 500 errors. They were just seeing slow performance and dropped connections.
And how did the companies try to fix it?
The response is really fascinating. AWS tried to mitigate the problem by withdrawing certain BGP advertisements.
Okay, let's break that down simply. What does withdrawing a BGP advertisement mean?
So BGP is the internet's map maker, right? It tells routers the best way to send traffic. When AWS withdrew those BGP advertisements, they were basically telling the rest of the internet, hey, don't send traffic down this congested road anymore. They were trying to reroute traffic away from the saturated links.
But if they closed one busy highway, where did all that traffic go?
It didn't just disappear. BGP automatically pushed it onto the next available link between Cloudflare and AWS. So the action, which was intended to help, actually made the problem worse at first because those secondary links weren't prepared for that massive sudden load.
Like closing the freeway and instantly flooding all the small side streets.
That's a perfect analogy. The incident required manual intervention, with the operations teams from both Cloudflare and AWS having to coordinate to find and throttle the single customer causing the surge. It's a great case study showing that even with distributed architecture, the connections between the big providers are still a major vulnerability.
Okay, so let's look at the second case study from the year, which actually shares the same root cause as the November event, the DNS resolver outage on July 14th, 2025.
This incident was maybe the most globally impactful in terms of just pure internet availability. It lasted for a critical 62 minutes. And DNS, the domain name system, is the phone book of the internet. It translates names like google.com into IP addresses. If the resolver fails, the internet just stops working for you.
Even if all the websites are technically still online.
Exactly.
So what caused this complete 62-minute global DNS blackout?
Again, it was an internal configuration error. It was strikingly similar in its mechanism to the November failure, but it affected a different part of their system, the 1.1 DNS resolver service. The mistake was in a routine change that was supposed to target a non-critical data service.
And that somehow took down the whole thing.
It did. This change inadvertently triggered a global network configuration refresh. But, crucially, the configuration involved older legacy systems that were used to manage the IP address for 1.1.1.1. And due to an old error, the update included instructions to globally withdraw the critical IP prefixes from their production data centers all over the world.
So a bug in an old system, triggered by a routine update for a totally unrelated service, was instantly pushed out globally and effectively hid the internet's phone book for over an hour.
Precisely. The postmortem really highlighted a severe lack of what we call progressive deployment. A change this big should have been rolled out slowly to one region, then observed, then a few more, a canary deployment. Instead, the flawed change went global instantly, which just shows a systemic flaw in their change management process.
And finally, let's look at the dashboard and API outage on September 12th, 2025. This one was a bit different, right? It gave us a clue about good architectural design.
It did. This was a classic control plane failure that was thankfully contained. The root cause was a seemingly small bug in a newly released version of their dashboard, specifically in the code running in the user's web browser.
You mentioned a technical term, a React use effect hook. Can you explain that simply for us?
Sure. In modern web development, you use software hooks to tell the browser when to do things, like get new data from an API. Think of it like a sticky note for a digital assistant that says, run this task whenever this specific thing changes. In this case, a developer accidentally put a problematic object in the condition list for that hook.
Okay.
Because that object was constantly being recreated by the software thought the condition was always changing. So instead of making one API call when the dashboard loaded, the function just ran the API call over and over and over in a continuous loop.
It's like a faulty washing machine timer. It was supposed to run the cycle once, but because of a broken part, every time you looked at it, it started the whole cycle all over again, overwhelming the water pipes.
That is a perfect analogy. This looping API call immediately overran their tenant service API, which handles all the management requests. As a result, the dashboard and the control plane APIs became largely unavailable.
And this is the key difference from November, the website stayed up.
Yes, the separation of concerns worked. The sources confirmed that the problem did not affect the data plane. The edge nodes kept serving cached files and applying security rules correctly. This incident showed that when you properly isolate the management layer from the traffic serving layer, you can limit the blast radius. It's a defense mechanism that, unfortunately, failed during the November incident.
By the way, if you liked and interested so far, please don't forget to like, share, comment, and subscribe. So when we put all four of these incidents from 2025 together, the regional congestion, the global DNS failure, the control plane overload, and then the ultimate global degradation in November, we see a very clear pattern of vulnerability emerging. What's the recurring lesson here?
The data clearly points to two critical and recurring failure modes for this kind of hyperscale infrastructure.
Okay, what's the first one?
First, you have centralized configuration flaws. We saw that dramatically in the November and July incidents. This is where an internal software error, usually related to a change, just bypasses all the distributed redundancy of the physical network. The problem isn't the hardware or an external attack, it's the flawed logic that gets pushed instantly across the entire global fleet.
And the second failure mode.
Second, we have external congestion events, which we saw in the August AWS incident. Even with massive capacity, the physical peering links between the biggest providers can still be overwhelmed by a single customer's traffic surge if capacity planning isn't perfect.
These failures cost millions, even when they only last for a few minutes. So given these recurring systemic failures, what can companies who rely on these services actually do to protect themselves? It feels like relying on just one single vendor, no matter how big they are, is just an unacceptable risk now.
That is the ultimate strategic lesson of 2025. It's a mandate for a multi-vendor strategy for architectural decoupling. The economic impact is just too high to ignore.
So how does a company move from relying on just vendor A to a truly resilient multi-vendor setup? Where do you even begin with that kind of decoupling?
It begins with a comprehensive multi-CDN strategy. That means contracting with two or more independent content delivery network vendors. But the real challenge isn't just signing the contracts, it's the control mechanism. The logic that steers the traffic has to be handled by an independent global server load balancing, or GSLB system.
Can you walk us through what GSLB does and why it has to be independent from the main CDN?
Of course. GSLB is essentially the top-level traffic controller. It uses sophisticated algorithms to decide for every single user request which CDN vendor A or vendor B is the best choice at that exact moment. It bases that decision on performance, cost, and most importantly, on health.
And it has to be independent because of what we learned from the November incident.
Exactly. If vendor A's control plane fails, meaning their dashboard, their API, their internal health checks are all down, you can't rely on vendor A's own system to tell you that it's broken and to shift traffic to vendor B. A failing vendor cannot be trusted to report its own catastrophic failure.
So the company has to use a completely separate third-party system to act as the brain. How does that independent system know that, say, Cloudflare is having a data plane failure?
It uses advanced operational mandates, primarily automated synthetic monitoring and real user monitoring, or RUM. Synthetic monitoring means the GSLB provider deploys monitoring agents all over the world that constantly simulate user requests against both of your CDN vendors.
And they're looking for signs of trouble.
They're looking for those telltale degradation signals, like a sharp, sustained spike in HTTP 500 errors or a sudden drop in performance. Once the independent GSLB detects these failure signals externally, it autonomously triggers the failover. It updates the network routes and shifts traffic instantly to the secondary, healthy CDN vendor. And this has to be automated. Humans are just too slow.
Okay, so that handles the content delivery part. But the July incident showed us that the DNS layer is an equally critical point of failure. How do we build resilience there?
That's strategic mandate number 2, an independent multi-DNS architecture. The domain name system has to be fully decoupled from your content delivery and security layer. Enterprises must use multiple globally distributed DNS providers that have absolutely no shared infrastructure with their main CDN vendor.
Because if the primary CDN vendor fails, the ability to change your DNS records is your only lifeline.
That's it exactly. If Cloudflare's dashboard and API are down, an administrator has to be able to log into an independent DNS provider's control panel and update the DNS records to point traffic to the secondary CDN. or even directly back to the origin server in a worst-case scenario.
So you have to be able to manage your naming records even if the main provider is completely offline.
Yes. And this requires careful implementation. You really have two main options. You can run two authoritative DNS providers at the same time. Both are primary, both are actively serving records, but this requires the customer to manually synchronize the configurations between them.
And that sounds like it could be a heavy operational burden. How do you manage that synchronization?
It is a significant burden, no doubt. It requires a high level of expertise. Many large companies rely on automation tools for this, things like Terraform or OctoDNS. These tools let you treat your DNS configuration as code. You define the desired state once, and the tool automatically pushes those identical configurations to both of your independent DNS providers at the same time.
So it reduces the risk of human error.
It does. The alternative is a primary-secondary DNS setup. This is usually simpler to manage. The primary provider handles all the changes and then automatically pushes those updates to the secondary provider.
And what's the critical feature you need from that secondary provider in that kind of setup?
You need a robust secondary DNS override capability. Normally, the secondary provider just serves the information it gets from the primary. But during a failure, this override capability lets the secondary provider start responding with its own IP addresses, the IPs of the backup CDN. It ensures that traffic is still directed to a healthy network path.
This level of planning is clearly extensive. It really moves the responsibility for resilience away from the vendor and onto the enterprise itself.
That is the core lesson here.
Yeah.
Enterprises now must operate under the assumption that their vendor's dashboard and API will be non-functional during a major global incident. And that places the entire burden of a rapid failover onto external independent systems that the customer manages. If you fail to plan for that, you're giving up your ability to recover.
This look into the 2025 incidents has been incredibly detailed. It really strips away that comforting idea of the cloud and shows us this fundamental paradox of having centralized governance over these physically distributed networks.
It does. The key lesson for resilience is internal integrity. While these hyperscale distributed networks are engineered to be massively resilient to external attacks or physical failures, they remain acutely vulnerable to internal configuration changes. The centralized software layer that governs the massive global network, the control plane, is the single greatest threat for a simultaneous global failure.
So routine maintenance, internal bugs. These things pose a bigger threat than a massive DDoS attack.
They possess a global blast radius that can completely defeat the physical redundancy provided by a system like Anycast.
And as we wrap up, the vulnerability of the entire digital ecosystem just feels so amplified when you think about that self-referential fragility. The fact that the site most of us rush to during an outage down detector relies on the very same infrastructure it's supposed to be monitoring.
It does. It really underscores the massive concentration risk. When all these critical internet functions, security, delivery, even outage reporting are consolidated among just a few hyperscale providers, the systemic risk just multiplies. And that leaves us with a final provocative thought for you, our listener, to mull over.
Go on.
If the largest, most resilient networks on Earth can be brought down by a single internal configuration change, what steps can we as end users or as participants in this industry take to push for more diversity and more decoupling in the core infrastructure we all rely on? How do we break this centralized logical choke point?
Hope we could explain the concept and helped you understanding what are web clouds, how they're working, and what's the reason they're down sometime. We'd be appreciative if you like and share the video with your friends, also comment to join the conversation, and subscribe to the channel to help us grow. Wish you a good and online week with no interruptions. Bye for now.